Hello, sir. Warm greetings to you. I am Shreeya Kapoor. My registration number is 19BCT0231. My group members are Anirudh Sharma, 19BCT0166, Harteej Singh, 19BCT0168, Aditya Shri Sharma, 19BCT0171, and Ishika Goyal, 19BCT0232. We will be explaining the assembly language program to calculate the factorial of a number, including code and output, and the ALP to demonstrate block transfer using the string instructions. So, the first step after opening DOS box is mounting the DOS box to the current directory. So we write mount c colon hash 8086. This command will prepare the software to mount on C directory in 8086 folder. Now we'll write C colon. This command will change the directory to C. Now we write edit pack.asm. Pack is the file name and a file of this name will be created. So now the further code will be explained by Hartej.
In the first line, dot model small, we declared the program type to be small, which means the code segment, data segment, and the stack segment are used only once and their values will not be changed during the course of this code. Dot stack 64 and dot data are used to initialize the stack segment and data segment. We will be using a 64 KB stack. In the next line, we take the data segment input. A pointer A is created to point to data, which is 5 in hexadecimal. This is the byte in the memory. In the next line, we initialize the code by .code statement. In the next two lines, we start the address. Move AX, at data moves the 16-bit address value of data segment to AX register. AX register is just a medium because direct data transfer of 16-bit value is not possible to DS. Base address is moved in these two steps. The next step is LEA SI, A. LEA stands for load effective address. In this case, SI is source index register, and this statement is used to load the address of operand into SI. We have to move the effective address of pointer value. Move BL, content of SI. Here, an index addressing mode has been used in which the content of SI, that is the offset value of data, which we provided as 05 in hexadecimal, is transferred to BL register. The next statement, move AL, 0001 hexadecimal, is an immediate addressing mode because data is the part of the instruction. The data in this instruction is 0001 hexadecimal. The next we come to the main factorial logic. Mul BL multiplies AL register to BL register. In this iteration, AL register was 1 and BL was 5. So after this statement, AL becomes 5. In the next statement, DECBL, we decrement the value of BL register to 4. In the next statement, CMPBL, 0H, we compare the value of BL register to 0. Here, 0 is the immediate data. In this statement, if after comparison both the quantities are not equal, the loop will repeat itself. Hence, it will go back to mul BL statement. And similarly, the iterations will go on until BL becomes 0. Once they become equal, in this code, it will become after 5 iterations, the code will come out of the loop. Next statement, J and Z repeat, is a statement which takes the code execution back to repeat label where the multiplication starts. Next, move AH, 4CH is a statement in which the 4C hexadecimal value is stored in AH register. Int 21H is an interrupt statement. It checks if the value of AH register is 4C. If it if the value is 4C, then the program exits there, and the next statement, end, denotes the end of code.
Now we will save this file and we will exit fact.asm. After coming out, we write masm fact.asm. This command is written to compile our code. Further, in the next step, we write link fact.obj. This command will create an object of fact.asm and link that object to the fact.exe file, that is, it parses the fact.obj into fact.exe. The next command is debug fact.exe. This command is written to run our program step by step. Now, the further output will be explained by Aditya.
So using the command T, we'll trace each instruction of the program line by line. The first instruction is move ds, ax. This instruction will store the base address from ax in ds. Now the copy of ax is moved to ds and the offset address is moved to si. ds and si combined will generate a 20-bit address. The input value, that is 5, is now moved into the BL register. Immediate value 1 is moved to AL. We have 1 in AL and 5 in BL. The content of BL is multiplied with AL and the result is stored in AL register. So the current value in AL is 5. We'll decrement the value of BL. It changes to 4. And now the value of BL is compared to 0. If it is 0, the execution stops. Otherwise, it executes the above instructions again till the content of BL register becomes 0. So we'll wait till the value becomes 0. So you can clearly notice the content of AX register, which is 0078. If we convert it into decimal notation, we get 120, which is the factorial for our input, that is 5. Hence we get the desired output. At last we come out of the program using the instruction quit. So the explanation of second program will be taken over by Shreya, Ashika and Aniruddha.
So now we are moving to the second ALP, which is block transfer using string instructions. So the first step after opening the DOS box is mounting the DOS box to the current directory. So we write the code mount cc colon hash 8086, which prepares the software to mount on the C directory in 8086 folder. Then we write C colon, which changes the directory to C. Now we write edit trf.asm, which creates the file trf.asm. So now Ishika will explain the code of this program.
Okay. First, we will start with dot model small, which means you get a program where CS points to a segment of its own, followed by DS and SS are pointing to. The stack is placed in the highest region of the SS segment. From the next line, we will write .stack64, which is frequently used area of memory designated for functions to use as a temporary storage. Then we have .data, that is a section of program in an object file or in memory, which contains the global variable and static variable that are initialized by the programmer. Now we will create a string named string1 in the next line, followed by db, which means data byte, which allocates some space and fill it with a string. Then we will store the values in the string, which are 01h, 02h, 03h, 04h, and 05h. Now moving on to the next line, we will write string2, db, and we will have 4 duplicate binary zeros as a string. Now Anirudh will continue with the rest of the code.
Now, coming to the part that is to be executed by the processor, we start with move AX add data. This line moves the memory location of add data from the data segment to the AX register, which is the accumulator register. Now we have move DS, AX, where the data is moved from AX register to the standard variable DS. In the next line, we have move ES, AX, in which the memory location is moved from AX to the extra segment ES. This code word LEA is load effective address, and this line loads the effective address of string 1 into the source index. This next line loads the effective address of string 2 in the destination index. Now moving on to the remaining part of the code, move CX, 05H loads the data 05H into the count register, and CLD clears the destination flag and sets it to 0. While the destination flag is set to 0, it increments the value of SI and DI by some value. This line REP move SB is executed by repeating till the CX is 0. This command move SB, which moves the string to byte. Int3, int is not an integer, it's called an interrupt. Int3 creates a breakpoint, which is used by the programmers to create breakpoints while debugging the file. And this end and dot end ends the part of marks the end of the code which is to be executed by the processor, and halts the CPU till there is some other interrupts coming into it. Now I want Shreya to carry on with this.
So now we save the trf.asm and exit this file, and now we write the code masm trf.asm. This will compile our code. In the next step, we'll write link trf.obj. This will create an object of trf.asm and link that object to the trf.exe file. That is, it will parse the trf.obj into trf.exe. Now we write debug trf.exe. This will run our program step by step. So now the output will be explained by Ishika.
So now, since we have written the debug command to run the step-by-step program, we will use G and D to print the output to get the register values. So in the conclusion, after seeing the output, we can say the data has been transferred from one block to the other. Thank you.